Good morning, class. Welcome to this lesson on Modern 2, the photoelectric effect. Today we will be able to explain what a photon is and the photoelectric effect. Okay, so the photoelectric effect, a little bit of history, is what Albert Einstein received his Nobel Prize in. Okay, this was his idea. Okay, and he had a lot of amazing ideas, which is why he is known as being one of the smartest men alive. But the photoelectric effect is what he received his Nobel Prize in. Okay, and basically, the idea of the photoelectric effect is what gave evidence that light consists of photons. This idea of the photon. Okay, so what is a photon? A photon is a discrete packet of energy. Is a discrete packet of energy. Okay, so photons, light consists of small packets of energy. And so we have to really think about what you probably heard about this in other classes and whatnot, but think about our wave theory. We have always seen waves as transmitting energy in a continuous stream from one area to another. So we see it as a continuous stream. Now, with this idea, this continuous stream is really like a bunch of little packets of energy in a stream. So this is where we're talking about the duality of nature, okay, and the fact that waves can exhibit particle-like behavior because light is a wave. Light is a wave. And before this, no one would ever have thought light comes in these tiny little amounts. We always thought it was just continuous. It was just one beam of light that just keeps on going. But now we realize that it comes in these little packets, which is pretty cool. And these little packets are going to be defined as energy. The amount of energy in a little packet, the amount of energy in a little packet is going to be defined as Planck's constant times F. And this value of H, like I said right now, is Planck's constant. We're going to talk about Planck in a little bit in a few more videos and what this number really means. And um, usually teachers cover Planck's constant first before getting the photoelectric effect. I find that covering the photoelectric effect first and getting the idea for this concept of discrete packets of energy is better, and then going back and talking about where this number came from. So most books, most lecturers go through Planck first, then the photoelectric effect. I find it's better to go a little bit backwards. So we all know that waves, any wave, any EM wave, we know that any EM wave has a frequency, okay? It doesn't have to be visible light. Any EM wave has a frequency. And so all these EM waves are going to be in discrete packets of energy that are going to be defined as this number times F. And Planck's constant is 6.626 times 10 to the negative 34th joules per second. And you can see here, if H is joules per, joules seconds, and frequency is 1 over seconds, those cancel out and give us joules. So this is going to be one of our main formulas for this chapter, is this concept of energy equals HF, okay? Just like in mechanics, it was F equals ma, and in waves, it was V equals lambda times frequency. Now it's going to be E equals HF. This is going to be our pretty much our base equation, okay? So the photoelectric effect. Let's think about what this means in terms of discrete packets of energy. What they found is they were shining light on metal. They were shining light on metal, okay? Not a big deal, shining light on metal. Well, let's say they're shining light on a piece of metal at a low frequency. okay, at a low frequency. As we can see here, E equals HF. So if we have a low frequency, it's going to be low energy. Okay, low energy. So we have low energy light shining on a piece of metal. Nothing happened. Nothing. When we started increasing the frequency, so now we have a high frequency light. So that means high energy shine on a piece of metal. Electrons were ejected electrons were ejected from the surface. So electrons started leaving the surface of the metal. So how this brought about the concept of photons is very simple. If light was a continuous stream, that means if I slowly increased it, if I slowly increase the intensity of light, then I should slowly see more electrons ejected. Okay? I should slowly see more electrons ejected. And let's go back a second to make sure we understand what's going on. We have metal. Metal's made of just a bunch of nuclei. Okay, so here's a metal nucleus. Around it is an orbiting electron. Okay, the positive charges in the nucleus are keeping the negative electron close to the nucleus. And if we hit this with some energy, it's going to absorb some energy, and we know that if it gets more energy, it's going to move faster. So now we have a faster electron. And if this thing moves fast enough, if this thing starts moving fast enough, the orbit's going to increase a little bit, and what would happen is this thing would just leave. So it gets more energy, it's going fast, it's going to break away. The force holding it in can't hold it anymore. Okay, so let's make sure we have that idea in our head as we're talking about this. Okay. So if I slowly increase the intensity of light, I should slowly see more electrons ejected. But that didn't happen. What happened was as we increased frequency, all of a sudden we went from no electrons ejected, we got to a certain point based on the metal, and all of a sudden we started seeing a lot of electrons ejected. So we went from nothing to a lot very quickly. So that's very odd. If energy was a continuous stream. Let me give you another analogy before I finish this up. Pretend you have a ball and you're trying to throw it up and you're trying to get it on top of this ledge. Okay? You have one throw. And once you let go of that ball, it's either going to make it or it's not going to make it. Okay? You have one shot at it, okay? You can't throw it in the air and then slowly give it more energy to make sure it gets to the top, okay? There's not a continuous flow of energy to get this up. You throw it once, you gave it its energy, it's either going to make it or it's not going to make it, okay? And that's kind of the same with light. An electron orbiting a nucleus receives a certain amount of light. Okay, it receives a certain amount of light. This electron needs a certain amount of energy. Because this electron absorbed one photon. Okay, so from this one photon, it's going to absorb it. If the photon, like the throw, was enough, the electron will be ejected. It'll leave. If the photon isn't enough, it won't leave. Period. And this amount of energy is based on the frequency. It is based on the frequency. So each individual electron that was leaving the metal, you can see from this picture here, electrons are leaving the metal, had to come from a certain frequency of light. If that frequency of light wasn't enough, if it didn't have a certain amount of energy, it wouldn't leave. Because the classical thinking was before this, if I have back in this picture right here, if waves are a continuous stream of energy, if waves are a continuous stream, even if the wave hit it, it should still gain more and more and more energy because a wave is a continuous flow of energy. But it is not a continuous flow of energy. The energy comes in packets. And because it comes in packets, either there's enough or there's not enough. Okay, so either there, and so just like the throw of the ball here, either it's going to make it up or it's not going to make it, but you only get one shot. One photon is going to be absorbed, and that's going to be it. Okay, so this was a big deal because it really confirmed this idea that waves are going to act like particles because waves come in packets. So if they have discrete packets, just like this ball over here has a discrete mass, then we can start treating it like a particle. So that is the photoelectric effect.